Hey everyone, this is our study of momentum and collisions, and so it's going to be in our energy unit here because they're all pretty closely related. So the first thing I want to talk about is what momentum is, and I know we've all heard about it, and we'll talk a little bit more in class. But momentum is a quantity of motion, that depends on both the mass and the velocity of the object in the question. And so a lot of times we, especially when we first started, we would talk about, it's going, right? And something has to be quantified by its movement. Well, this is where momentum comes in. And so it has both mass and velocity here. And so the units are kilogram meters per second or a Newton second. That's going to be interesting. We're going to be able to use that as we work on some equations also. So momentum is a vector quantity, so we can have that same kind of idea that it's positive to the right, left is negative, that kind of thing. So we're going to be able to add and subtract them. That's going to be important. So the first example is pretty straightforward here. We have a baseball being pitched at 32 meters per second, and the batter crushes it, and the ball leaves the bat faster than it came in. So what is the ball's change in momentum? So pretty straightforward. The change in, right, is the delta P. And so we always consider that the final minus the initial. And the P is the unit of momentum. It's kind of weird, but that's what we're going to use. And so what happens here is we have to understand that the ball is coming in at one direction. So here's my initial velocity. The ball is hit, and then it changes direction. So the signs definitely matter here for us. So when we take a look at our equation, we have mvf minus mvi. And since we were terrific math students, we can factor this. And this is what we'll get here. So we can plug in. Notice what happens with the signs, though. So the mass is, I think, is it 0.01 kilograms? Yeah, sorry, I forgot that. The mass is 0.01 or 0.1 kilograms. So 0.1 kilograms. The final velocity, it looks like it's going the positive direction, the way I drew it. So that's 48 minus the negative 32, right? This initial velocity was pointing in the negative direction. So when you calculate that, we get a positive, right, 8.0 kilogram meters per second, or you can say to the right. And so it's going to be important that the sign matches the direction of the ending momentum or the beginning momentum. So when we say this, we're going to say left is typically going to be negative, and then to the right is typically going to be positive. If we can just keep the same convention, it makes doing the problems a little bit easier. So that's a basic intro to momentum. We'll have a lot of questions that'll involve these kinds of ideas. Impulse is an interesting idea. So impulse is a change in momentum. And so we denote that by using the capital I equals the delta P. So we have a couple of different ways to say that. Since we have mass and velocities being involved, and then we had that idea of a Newton meter second, we can express momentum in a couple of different ways. So the change in momentum, first off, is basically mass times the delta V. So that makes sense. There's a delta there. And then we have this idea of a force acting on it for a certain amount of time. And that's going to be important. You know, forces haven't gone away. So we have all of these ways to express this change in momentum, right? So a quick derivation here looks something like this. Delta P is equal to m delta V. Well, delta P is mass, and then velocity can be written as an acceleration times time. Well, what happens here is that now I can substitute that mass times acceleration. Well, it becomes force, and time remains. So remember, the units are a Newton second, or a kilogram meter per second squared times a second. leaving me with a kilogram meter per second, right? So that's just kind of a quick way to show where these equations come from. They didn't just kind of pop up, right? So let's go on to the next slide here. A couple of conceptual questions here. So someone jumps off the desk, they land, they bend their knees on the impact. Does it help prevent some serious damage to their knees? Why or why not? So what happens here is we can look at this from an equation standpoint, see if it makes sense this way. This mass times delta V, right, that change in momentum, that piece is going to remain constant. Right, this chunk right here. What happens is the two variables we kind of get to change are these over here. So for example, if I bend my knees when I land, what I'm doing is I'm increasing the time it takes for me to stop. What essentially happens is because the purple thing remained constant, that m delta v, the amount of force my knees see actually ends up going down. That's kind of cool, right? So second example here, same kind of thing, follow through with the ball, right? We've all kind of heard that, follow through if we're on the court or the field or something like that. So same idea, we have m delta v is equal to force times time. And what's happening here is what we're telling our athletes is essentially saying the amount of force we're producing on the ball or whatever ends up remaining constant. And the mass of whatever implement we're working with tends to remain constant. So what happens is if I can increase the time on the ball or the implement or whatever we're working with, right? If I can increase that thing, what tends to happen is whatever object I'm hitting, a ball, person, hitting a volleyball, something like that, the velocity ends up going faster. So that's why we tend to say follow through and don't stop short, those kinds of things. Okay, so I'll leave it to you guys to take a look at this car example, and we'll talk about it in class. So once again, m delta v is force times time, and we'll talk about this, like how does that make it make sense? And the same thing with this beanbag idea. We'll use the slam ball in class and take a look at that. So here's some calculations we can work with. So football, here's a question. So running in, calculate the impulse felt by the fullback versus the impulse felt by the tackler. Okay, so here's how we do this. So part A. We know that the impulse is the change in momentum, so delta P is equal to m delta V. All right, so we can use the mass given, 115 kilograms, right? So the final speed is going to be 0, right? We're stopping him, while his initial speed is 4.0 meters. Remember, this is pointing to the east, so if I look at my compass rose, it's negative, okay. So I end up getting negative 460 Newton seconds, okay? So that's where he's going. That's the impulse felt by the fullback, right? Part B asks what the other guy feels. So what's interesting is we can use this idea here. Delta P is force times distance, and Newton's third law still applies here. This force is equal and opposite, and the amount of time everything happens remains the same. So what happens here is we can say, well, this is just 460 Newton seconds to the west, or the other way, because this previous question is actually pointing to the east. So sometimes Newton's laws can help us work around some questions that might be a little tough, right? Part C, the average net force felt on the tackler. So we can say this, delta P is equal to force times distance, times time. Solving for force gives me F equals delta P over T, plug in what I know. So the average force felt is about 613 newtons. So there's that kind of example. Here's another one that is a little trickier in terms of some of the math that you have to do. But once again, knowing vectors is going to really help us out here. So in this particular question, we have a car traveling east, and then it turns due north. Okay, so we have to kind of manage what that looks like. On this question, we have a 1250 kilogram car traveling east, turns due north, and continues on at 15 meters per second. So it's pretty tempting to draw the triangle that looks something like this, going here and here. But what we have to do is we have to make sure we understand the rest of what's going on with the question. Here, it's asking me about the impulse that's going on. So the first thing I want to do is I'm going to look at this and say, okay, so the impulse is the change in momentum, which means it's the mass times the delta V. So I know what the mass is, but this delta V is kind of tricky here. If we remember back to our vectors, delta V means the final velocity minus the initial velocity. So in order for me to draw what that looks like, what happens is my final velocity is actually 15 meters per second going in the north direction, while my initial velocity is 25 meters per second due to the east direction. So if I draw it this way, it looks like I have final velocity pointing up. There's my 15. And then my initial velocity, it's negative 25. So it is actually pointing to the left. Here's my 25. This delta V here ends up being the resultant vector. So delta V looks like it's going to be whatever this ends up being. So 25 squared plus 15 squared. Do a little Pythagorean theorem here. So delta V is equal to 29.15 meters per second. I'll probably need to use this angle in here, right? Because this is where the impulse or that thing is pointing. So we can use our inverse tangent. 25 over 15. So I'm going to get an angle of about 59 degrees west of north. So these ideas of directions and stuff is going to come back and haunt us for a little while. So to finish off the question here, the mass is 1250. My delta V, the magnitude of that delta V is 29.15. And so the impulse, or the change in momentum, there's a big number here. We should have rounded maybe, but here it is, 0.5 Newton seconds at 59 degrees west of north. So that's going to be how we do these momentum questions and all that, okay? So what's basically the second half of these notes is the law of conservation of momentum. So we'll talk a little bit more in class. I want to go in a bit more depth about what some of these ideas mean, but if something is a closed system, that means something is always conserved. And so most of the systems we talk about will be closed, right? But there are ways to talk about it where they're not closed, and we'll discuss that in a little bit more detail. But one of the main ideas that I want to make sure we get across is that, like energy, momentum can also be conserved. So there's two different ways to think about it. So the first major way is, wrong pen here. The first way is that the initial momentum must equal the final momentum. And so one way to think about it is this. I can have, let's say, M1 V1 prime, right? That's kind of like the initial side, equal plus M2 V2 prime. these will all be the initial things, right? It's going to be equal to the M1 V1. You'll see it written like double prime plus M2 V2 double prime. And that's just another way of saying final for those guys. So either prime or initial kind of means the same thing. The second way to think about this is that the change in momentum in the total system here ends up being zero, right? If you subtract what you started with, you should get zero, okay? So when we talk about this idea of conservation of momentum, what typically we study are collisions and the types of collisions that we work with. So in an elastic collision, we have this idea that an object, kinetic energy is conserved, right? So elastic collisions, kinetic energy is conserved because the initial kinetic energy is going to equal the final kinetic energy. Okay? The other way to think about it is in inelastic collisions, and what happens is, so under conservation, things bounce off of each other. Right? They don't stick. But when we consider an inelastic collision, kinetic energy is not conserved. In other words, the things stick together. What happens though, momentum is always conserved. And the total energy is also conserved. What happens is some of our questions will realize that some energy might be quote unquote missing, but we can say that is that's due to heat, okay? We'll talk about this question a little bit in class, beginning of class, as kind of we're working on this, okay? But the last thing I want to do is work on a couple of example questions. So here we go. So so two rugby players of equal mass collide head-on while traveling at the same speed. What is their final speed? So what happens is the same mass, same velocity, they end up getting a 0 meter per second, right? They end up sticking to each other. So is the energy conserved? Yes, total energy is conserved, but kinetic energy is not conserved, okay? Momentum is also conserved, right? We have some positive momentum going that way, minus that same initial momentum, we end up getting 0. So here's an example of these things that stick together. So I have one train doing this, and then I have this blue car, he's just sitting there, and then what happens is they end up sticking together. So once again, this is an example of an inelastic collision. And so this thing has some initial velocity. The blue thing has a 0 initial velocity. And then what ends up happening over here is these two things stick together. So our equation looks something like this. M1 V1 plus M2 V2, right? We're using conservation of momentum here, is equal to these two things that are now stuck together times V3. Well, we can obviously see that that's going to end up dropping out. So my equation ends up looking like this. M1 V1 equals that total mass. Now they're stuck together again. V3. And so when you run the calculation, we should get something about 6.4 meters per second, and it's pointing in the eastward direction. Totally cool. All right, so that's a quick way to look at these inelastic collisions. Let's take a look at an elastic collision now. So we have a proton traveling at a certain distance. It collides with a stationary proton and then comes to rest. So we got to figure out what the final speed of the thing is. So what happens is here's my proton, and he's traveling with a certain velocity. The other proton, he's sitting there at rest. They collide. So in theory, because they're the same mass, that original proton ends up stopping, and then that proton that was initially at rest starts traveling with the same velocity. So the final speed should be 2 times 10 to the third meters per second. So kinetic energy is conserved at this point, which means the initial kinetic energy must equal the final kinetic energy. So a quick example is a little alpha particle traveling. It has approximately 4 times the mass of a proton. So a proton is traveling to the right, strikes it, and then rebounds at whatever, right, 1920 meters per second. What is the final speed of the alpha particle? So the easiest thing to do on these is to make a quick sketch of what's going on. So here's my proton, just sitting there, traveling at 3,200 meters per second. Here's my little alpha particle. He's kind of a big guy. They collide. So over here, this is the before side. And here's over here, here's the after side, okay? What happens is the proton ends up bouncing off of that larger alpha particle at 1920 meters per second. Then the alpha particle, and what we like to do is I'd like to kind of sketch to scale as close as we can, whatever this velocity is. So I'm going to say v sub alpha. We don't know what that is. So first thing I want to do is I want to use the conservation of momentum. m1 v1 prime plus m2 v2 prime, right? That's the total momentum before equals the total momentum after. So m1 v1 double prime, right? That's just the after, plus m2 v2 double prime. Originally, that alpha particle is not moving. We're looking for this guy right here. So we can build a little equation here. Looks like I'll have m1 v1 prime minus m1 v1 double prime over 4m1. That 4m1 is that alpha particle that is 4 times as massive as that other guy. So it's a bit of a shortcut there. Hope it's not too confusing. Equals the v2 double prime, or the speed or the velocity of the alpha particle after the collision. What happens is that one of the reasons we did that is we weren't given the masses, right? But what happens is if I do everything in terms of m1, everything gets to drop out. Yay, math. So we get a velocity of about 1280 meters per second in the positive direction, or to the right, whichever way you decided to say it. That's how we're going to do that, okay? The last type of collision is basically an explosion. So an explosion is just an example of a conservation of momentum, right? So here's my papaya. There's this. The initial momentum of this guy ends up being 0. What happens is the papaya has exploded, and so now these two pieces are going in these opposite directions. What happens is I don't know the mass of that first chunk, but I do know its velocity. I end up knowing the mass of the second chunk, and I know its velocity. So I can generate a quick equation here. The before momentum ends up being 0, while I have this m1v1 plus m2v2 idea. Then a little bit of algebra here. I can move things around. I can get negative m2v2 equals m1v1. This turns into negative m2v2 over v1 equals m1. And that's what we were looking for this guy right here. So if I run the calculation, I should get about 3.9 kilograms for the M1 piece, or that chunk that was missing before. One of the things to be sure about though is when I plug this in, this guy has to be negative for this right here. Ends up, or otherwise I would get a weird negative mass in there, and that wouldn't quite make sense. All right, so here's our video notes. To make sure you have any questions, let me know. I'll catch you later. Thanks, bye.